Hey everybody, this is Kevin Wallace, double CCIE and Cisco Press author, and in this video you're going to learn how to configure quality of service settings using MQC, the Modular Quality of Service command line interface. You see, these days it's become just so easy to set up quality of service. We can configure things with something like the APIC-EM's EasyQoS feature, which is what you see here on screen. But whether you're using AutoQoS for VoIP or AutoQoS Enterprise or something like EasyQoS, the configuration that's going on behind the scenes is using a three-step process called MQC. Again, that's the Modular Quality of Service command line interface, or the Modular QoS CLI MQC. And in this video, I want to show you how we can configure things or verify things using MQC. You see, the challenge is we can go into an interface like this and say, what is business relevant, what is default, what is business irrelevant, and we can take some assumptions, which we can tweak, by the way, but we can take these assumptions and something like EasyQoS inside of an APIC-EM controller is going to deploy a very robust quality of service configuration out to our routers or switches. And while that's great, my concern is there are so many network engineers out there today that don't know how to interpret those automatically generated configurations. They don't really know what's happening when they look at the configuration. They're not able to tweak it themselves. And I want to fix that here in this video. Let's jump into a discussion of the three-step MQC process. But before we see exactly what we can configure with MQC, let's take a look at some of the quality of service tools in general, most of which are configurable with this MQC process. First, let's talk about classification and marking. We can configure that with MQC, among other ways, but we're going to focus on MQC in this video. Classification and marking, I compare this to getting on an airline. When I board an airline, I typically am in something like Zone 3 or Zone 2. I don't get on the airplane very quickly, in other words. Now, I'm a member of the Delta Frequent Flyers program, but I'm not yet there. I haven't earned my medallion status or whatever it is that lets me get on the airplane early. But imagine the day comes. I finally earn my frequent flyer status, and I walk up to the gate agent, and they say, Mr. Wallace, before boarding the plane, can you prove that you're a frequent flyer? Can you produce your boarding pass from the time that you went to Orlando, the time you went to San Diego and San Jose, and the time you went to Dallas and Chicago? That would be terribly inefficient, wouldn't it? To have to prove every single time I got on an airplane that I really was a frequent flyer. So what do they do instead? They mark it on my boarding pass. I hand them a boarding pass that says something like priority boarding or whatever code they use, but they put a marking on the boarding pass to indicate that I am somebody that has reached frequent flyer status whenever that day comes. And that's what we're going to do with our network traffic. Instead of trying to run some sort of an access control list every single time a packet goes into an interface on a switch or a router, instead of doing all that heavy lifting each and every time, let's just do it once. Cisco recommends that we classify, we recognize what kind of traffic a packet is very early on in its travel, as close to the source as possible. And then we can apply a marking. And then the next switch or the next router can very quickly, very efficiently look at that marking and make a decision, like a forwarding decision or maybe a dropping decision based on that marking. That's classification and marking, but just marking a packet by itself, that does not alter the packet's behavior. We have to have other mechanisms that can take a look at that marking and then make a decision, like I said, dropping it or forwarding it based on that marking. One such quality of service mechanism that can interrogate a marking and then make a decision based on that marking is queuing. Now, queuing comes in many different flavors, but when we're configuring MQC, the two primary types of queuing that we'll be using are class-based weighted fair queuing and low latency queuing, or LLQ for short. With class-based weighted fair queuing, we can define all these different classes of traffic. Now, Cisco cautions us not to define more than 11 classes of traffic ourselves. There is one default class of traffic. We did not create that. We cannot delete it. It's just there. It's sort of the catch-all class. If we don't classify traffic into a class that we create, it is going to be classified into that class-default class of traffic. But we can have, with class-based weighted fair queuing, we can have a separate sub-queue for each class of traffic to separate them. Just to give you a super simple example, let's say that we've just got two different classes represented by the two buckets here on screen. And imagine a router that has a gig link coming in from the local area network. And then it's got a relatively slower speed WAN link going out, maybe, let's say 10 meg going out, but we've got a gig coming in. That's a big speed mismatch. What happens if we're just flooding traffic into the router at a gig rate or approaching a gig rate, and we're trying to go out on this relatively slow 10 meg link? Well, obviously that speed mismatch is going to cause an issue, but what the router is going to do is allocate some memory called a buffer or a queue on that output interface. And it's going to store up those packets temporarily until hopefully in a moment WAN bandwidth demand is going to die down. Then the router can take the packets out of the queue and send them on their way. Now, what if we took that queue and divided it up into different buckets? That's what we've done here. We've got a voice over IP bucket, or a sub queue, and a best effort. In other words, everything else goes into this best effort bucket or best effort sub queue. And we put voice over IP in one and everything else in the other. And let's imagine that there's a big data burst on the network. Well, the queue space, that buffer size on an interface, it's only so big. It's only going to hold so many packets. But we're putting our voice packets in the voice over IP bucket, which has a certain capacity, and we're putting everything else in the best effort bucket, which has its own capacity. You see, it's possible that a big data burst might overflow the best effort bucket. We're dropping packets there, but we're not dropping voice over IP packets because there's still room in the queue. There's still room in the bucket for this category of traffic that we've classified and maybe marked as voice over IP traffic. That's what queuing does for us. In times of congestion, queuing can help make sure that traffic that we've deemed necessary to get out does get out, and we can influence how much bandwidth that it has access to with our queuing mechanisms. Now, low latency queuing, it's very, very similar to class-based weighted fair queuing. The big difference is it's got an extra queue on it. It's got something called a priority queue, which means anything that we put in that priority queue gets to go first, up to a limit. It's like a carpool lane. In a lot of major cities here in the US, we have carpool lanes. So if there are two or more people driving together, then they're classified as carpool traffic, and you get to go over in that carpool lane. If you've ever watched carpool karaoke, you know the guy's always picking up somebody that he ends up singing with, and the reason he's picking them up is so that he can have two people in the car and he can drive in the carpool lane. That's why it's called carpool karaoke. But imagine our voice traffic is being in that carpool lane. It's special traffic. It gets to go ahead of other traffic, but there's still a speed limit in that carpool lane. We can only go so fast. Same thing here. We don't want our voice traffic, even though it gets to go first, it only gets to go first up to a certain amount of bandwidth. We don't want to starve any other traffic out. So we're going to say, all right, you get to go first, but you cannot consume more than this amount of bandwidth, maybe this percentage of an interface's bandwidth, so we don't starve anybody else out. That's queuing. Next is congestion avoidance, sort of the flip side of queuing. With queuing, we were trying to make sure that we had at least a minimum amount of bandwidth for different types of traffic. With congestion avoidance, we're trying to prevent a queue from ever filling to capacity. You see, there are some really negative side effects that happen if that interface's queue ever fills to capacity. Imagine it. It's full. There's room for nobody else to come into that queue. We're starting to drop all sorts of traffic, high priority traffic, low priority traffic. It doesn't matter. It gets dropped. So that's a really negative side effect. But another more insidious side effect that's not as obvious is the way TCP flows work. When you were first learning about TCP, do you remember the concept of a sliding window? A TCP session is going to send a segment to the other side, and then it's going to get an acknowledgement. And then it's going to send 2 segments and it gets an acknowledgement. And then it sends 4 segments and then 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, 16384, 32768. And that's as high as I remember off the top of my head. But it keeps doubling its window size as long as it receives an acknowledgement asking for the next segment in this flow within a certain amount of time. Well, if we drop a packet, which we would if the queue fills to capacity, suddenly the TCP session realizes that, oh no, I'm sending too fast. I'm sending too aggressively, and I don't want to drop packets, so I'm going to back off. I'm going to start sending at a slower rate, and it's going to back off its window size, resulting in a less efficient use of bandwidth. In other words, we're spending more time waiting for that acknowledgement instead of actively sending traffic. Well, that's bad enough if it happens to one TCP flow, but imagine if the queue is full, then all of the TCP flows almost simultaneously are going into TCP slow start because they're all dropping packets. That's not good. we can use a congestion avoidance mechanism called weighted random early detection with our Cisco routers. And what weighted red for short is going to do, it starts to get nervous once the queue depth exceeds a certain level. And as that queue depth continues to creep up and get higher and higher, we get more and more nervous. And at a certain point, we introduce the possibility, not the guarantee yet, but the possibility that we're going to be discarding particular markings. We might say, if you have, we'll not get into DSCP markings in this video. I did that in a different YouTube video that you can check out. But let's say that we've got a DSCP marking of AF31. And we might say if the queue depth gets greater than, let's say 25 packets, we introduce the possibility of discard. We're not necessarily going to be dropping everybody that has that marking, but it's possible. And then as the queue depth gets greater and greater and greater, we increase the possibility of discard until we get to a maximum threshold. And after that, there is a guarantee that if you exceed this certain threshold, and if you have this particular marking, then there is a 100% probability that you're going to be discarded. And you notice I have a picture of the Vulcan hand symbol meaning live long and prosper on the screen. And it's because what we're talking about here, straight random early detection, reminds me of my favorite Star Trek movie, Star Trek II, The Wrath of Khan. You might remember it. Ricardo Montalban played Khan, and he's about to blow up his ship, and it's going to destroy the Enterprise too. And Spock goes down into main engineering to get the ship where it can move again and get out of the way of the explosion. And to do that, he has to go into this chamber that's filled with radiation, and he becomes blinded. And Kirk goes down to check on him, and Kirk goes up to the glass where he can see Spock, and he says, "Spock!" And Spock comes to the window and says, "Ship out of danger?" And Kirk says, "Yes." And they go on to have this conversation where Kirk is asking him, "Why did you do it, Spock? Why did you give your life to save the Enterprise?" And Spock says, "Don't grieve, Admiral. It's logical. The needs of the many outweigh the needs of the few." And Kirk says, "Or the one." That's what random early detection is doing. Random early detection is sacrificing a few of the flows. We're dropping packets from a few of the flows so that all of the flows do not have to simultaneously go into TCP slow start. And while there's a lot of value in doing random early detection, what we're going to be doing on our Cisco routers is weighted random early detection. Weighted red, WRED. We can set that minimum threshold where we introduce the possibility of discard. We introduce the possibility of discard at different levels for different markings. For example, AF41 does not introduce the possibility of dropping when a packet marked with AF13 comes along. AF13 is going to introduce the possibility of dropping before AF41. Again, I've got another video on my YouTube channel that really gets into how those markings work if you want to go check that out. But that's the primary way that weighted red works. We prevent a queue from filling up by starting to drop packets somewhat randomly, somewhat based on the markings, in an attempt to prevent the queue from ever filling to capacity. But we're still dropping packets, so it's kind of bad news for those frames that we are dropping. They've got to be retransmitted, and we have to go into TCP slow start for those sessions. An enhancement to weighted red is called explicit congestion notification, or ECN. What this is a kinder and gentler way of reducing our window size without violently throwing out packets. This is a way for us to say to the far end of the connection, "Hey, you're sending a little aggressively. Would you mind voluntarily slowing down? Would you mind voluntarily decreasing your window size so that I don't have to drop you?" And it says, "Oh, I'm so sorry. Of course, I'll voluntarily reduce my window size so that you don't have to drop me." That's an enhancement to weighted red that also falls under that congestion avoidance category, and it's something that I'm going to show you how to configure with MQC. Next, we've got a category of QoS mechanisms called traffic conditioners. And the two big mechanisms that fall under this category are shaping and policing. Both of these are different approaches for setting a speed limit on traffic. We don't want to send traffic too aggressively. We don't want a network gaming application, for example, to consume too much network bandwidth. So we can set a speed limit on that. We might have a situation where we have limited bandwidth and guest Wi-Fi access. Well, we might limit or just deny Netflix traffic, as an example, to keep the bandwidth down. We can do that with policing and shaping. Now, what's the difference? Well, policing is a bit more harsh. I've got the bowl of soup on screen to remind me of that Seinfeld episode where if you don't order soup correctly, the guy says, "No soup for you, come back 1 week." That's what policing does. If we try to exceed this speed limit, called the CIR, the committed information rate, if we exceed that speed limit, policing says, "No bandwidth for you, come back." Literally, it says come back. It drops a packet, forcing a retransmission. And Cisco recommends that we use policing on higher speed interfaces. They recommend we use shaping on lower speed interfaces. Now, here's what shaping does. When we exceed shaping's CIR, its bandwidth speed limit, it says, I'm so sorry, there's simply not enough bandwidth to send you at the moment, but please don't go anywhere, just have a seat. And here in a moment, hopefully the WAN bandwidth demand is going to die down, and then I'll come get you, and you can go on your way. So while policing is dropping traffic very aggressively, causing retransmissions, shaping is simply delaying traffic, letting traffic hang out in a waiting room until bandwidth demand dies down, and then we take it out and we send it on its way. And we can set up both policing and shaping using, you guessed it, MQC. And the final category of quality of service mechanism we'll talk about is link efficiency. We're trying to make the most efficient use out of a relatively limited WAN bandwidth. And a couple of major tools that fall under this category are link fragmentation and interleaving, LFI, and compression. First, let's talk about LFI. Imagine that we've got a relatively low-speed interface. Just to give you an extreme example, I know this is extreme, but just to make the point, let's say that we've got a 56K interface, 56 kilobits per second, can you imagine? And I'm trying to send a big data packet, a 1500 byte data packet, out of that 56K interface. Do you know how long it takes to do that? It takes about 214 milliseconds. Now, if I had a little tiny voice packet trapped in behind that massive data packet, it would be delayed by 214 milliseconds before we ever began to transmit the little tiny voice packet. That's a horrible delay. That's going to destroy our voice quality. So what's the fix? Well, the fix is LFI, link fragmentation and interleaving. As an illustration, notice the tractor trailer that I have on screen. This is a tractor with a couple of trailers behind it. And there are some in the United States that have 3 trailers behind them. They're called longer combination vehicles, or LCVs. These triple tractor trailers, I've never seen one here in the part of the country that I live, but in some of the flatter states you see those. But imagine, I'm stuck at a traffic light behind one of these big triple tractor trailers. And let's say I'm in a little tiny sports car, and the traffic light turns green, and the first trailer goes through the light, and the second trailer, and finally the third trailer, and the traffic light probably turns red again before I get a chance to go through. The idea is that I'm being delayed by this big payload trying to get through the light, through the intersection. Well, that's analogous to a big data packet trying to get out of an interface, going really, really slow. But what if I took that big triple tractor trailer and I separated the trailers, and I put a tractor in front of each of those, and now I've got 3 single tractor trailers, 3 separate vehicles? Well, in my little sports car that's nimble and agile, I could probably weave in and out. I could probably get ahead of 1 or 2 of those trailers. I could get out of the interface sooner. Well, that's what's happening with our data packet. With link fragmentation and interleaving, we're taking the big data packet and we're busting it up, we're fragmenting it, and then just like we're shuffling a deck of cards, we're shuffling in the little tiny voice packets in amongst the now fragmented data packets. And as a result, our voice traffic gets out of the interface sooner. However, we're not going to be using MQC to configure LFI, but I did want you to know about it. We can use MQC, however, to configure, well, what we primarily use it for is to do RTP header compression. You see, Voice over IP uses the real-time transport protocol, RTP, to send voice media. And if we're using a codec, a coder-decoder that compresses our voice, if we're using a codec of, let's say, G.729 is a popular example, then our payload may only be like 20 bytes. But the header, the combined layer 3 and layer 4 header, where we've got an IP header, a UDP header, and an RTP header, we combine all those headers, they're 40 bytes in size. The header is twice the size of our payload. That's a horrible ratio. So what we can do with RTP header compression is quote-unquote compress that 40 byte header down to only 2 or 4 bytes. It's 2 bytes without a UDP checksum, and it's 4 bytes with a UDP checksum. Assume on your Cisco gear that you're not using a UDP checksum. Assume it's going to be a 2-byte header. But notice I put compressed in quotes because we're not really doing compression. I know it's called RTP header compression, but we're not actually doing compression. What we're doing is caching. Here's what I mean. As we've got this RTP stream coming into a router interface, and if we've enabled RTP header compression, it's going to say, you know what? There's a lot of commonality in every single header. All these 40-byte headers I'm seeing, Every single packet has the same source and destination IP address. Every single packet has the same UDP port numbers. Every single packet has the same RTP payload type, because they're all part of the same session. So the idea is with RTP header compression, and we have to set this up at each end of the link, by the way, not just one, but we have to set it up at each end of the link. What we're going to do is make a copy of that redundant information of that header. And then we'll send a much, much smaller header, like 2 bytes. Send that across the wire, and when the other side gets it, it says, oh yeah, this is part of this session. I've already memorized, I've cached the layer 3 and the layer 4 header information. I'm just going to stick that back on to reform the packet and send it on its way. And as a result, we save a ton of bandwidth. I've seen this double. I've seen this actually, in a few cases, I've seen this triple the call carrying capacity across a WAN link. Now, you might wonder what's in that little 2-byte header. Well, it's called a session ID. That way we can distinguish between multiple voice over IP sessions. The question often comes up in class, hey, does this put a heavy processor burden on the router, all this reassembly? It used to, kinda, sorta, but nowadays, no, not so much. With the MQC way of doing this, it's pretty negligible. We can have as many as 1,000 RTP streams being reassembled. It's not really a concern anymore like it was when it was first introduced. Now we can set that up using MQC, however we probably don't want to in many cases. Cisco says that it's really not worth it if your link speed is greater than 2 megabits per second. Just don't bother, don't pay the tax, if you will, of having extra processor overhead. And for link fragmentation and interleaving, it really doesn't pay us to do that if our link speed is over 768 kilobits per second. At that point, because the triple tractor trailer, we put a tractor in front of all those trailers, we've got extra headers, in other words, in front of all those fragments. We are actually using more bandwidth than we were before. So it hurts us more than helps us if we get above 768 kilobits per second of bandwidth for LFI. So link fragmentation and interleaving, those are a couple of mechanisms, but we don't use them all the time. We use them when necessary on particularly low-speed links, and maybe only when we have specific traffic types, like voice as an example. All right, that's the overview of quality of service mechanisms. Now let's talk about how we can configure mechanisms in all these different categories using MQC, the Modular Quality of Service Command Line Interface. It's a 3-step process beginning with the creation of class maps. And again, Cisco says, thou shalt not create more than 11 class maps. So I guess we could technically have a total of 12. There's the class-default class map that we get by default, and then the 11 that we create for a grand total of 12. But if we do our job right, there's probably not going to be anything left to go in that default class anyway. But we can create, or should create, no more than 11 classes of traffic, because if everybody's special, if everybody's got this unique classification, then nobody's special. We don't want to be too granular in our classification, but we'll create some class maps. And then we'll take those class maps and they go into a policy map. And the policy map, that's where the magic happens. That's where we turn on these quality of service mechanisms. We're classifying when we do the class map, but we can do marking, we can do queuing, we can do congestion management, we can do policing, and we can do shaping. We can do RTP header compression, we can do weighted red, we can do explicit congestion notification, all inside of our policy map, and we turn it on a class map by class map basis. And once we've got this singular policy map that says how we want to treat traffic, we need to apply it somewhere. It's applied in step number 3 of MQC using the service-policy command. And we can apply this in either the inbound direction or the outbound direction, and that's very dependent upon which quality of service mechanisms you're using. For example, shaping can only be applied outbound, so not every mechanism works in every direction. And if what you've selected doesn't work, you'll get an error message about that. But we're going to use the service-policy command to apply this. Now, typically, we're going to apply this to an interface. There are some exceptions. You can get really fancy, and you can have nested policy maps where there's one policy map inside of another policy map. And there are some other places you can apply a policy map, but in general, we apply it to an interface. Now, I want to take you out live right now and show you how we can set up MQC to configure several of these quality of service mechanisms we've talked about. To begin, let's go into global configuration mode, and let's create a class map for our email class of traffic. Let's say we want to classify that. Let's say class-map, and let's give a little context-sensitive help here. there's some Boolean logic going on here. We've got match any or match all. And here's the deal. If I give multiple match statements, which I'm going to, I want to be able to match POP3 traffic, that's email. I want to be able to match IMAP. I want to be able to match SMTP. I want to be able to match Microsoft Exchange. Those are all email protocols or email applications. And if I say match all, then in order for a packet to be classified into this bucket, into this class map, then it would have to simultaneously match every single match statement. That's not possible. It cannot simultaneously be a POP3 packet and an IMAP packet and an SMTP and a Microsoft Exchange packet. That's just not possible. So I want to be very careful here and say match hyphen any, meaning that if I match any of the following match statements, then ding, 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 it's a match, and I get classified into this class map. Now, I'm going to give it a name, and I like to use uppercase names when I'm setting up my class maps. That way, as I'm looking through my configuration and I see something all in uppercase, like email, I realize that, oh, that's something that I named. That's not some sort of a Cisco iOS keyword. That's something that I came up with. Now I'm going to give a series of match commands. I'm going to say match, and by the way, there's lots of ways that we can match traffic, as you can see with context-sensitive help. Here's my absolute favorite way of doing it, though. I like to say match protocol. This is using something called NBAR, Network-Based Application Recognition. This does what's referred to as deep packet inspection. We can look into layer 7 information to recognize the signature or the behavior of certain applications. And we can recognize different protocols and applications based on their signature, not just based on port numbers. Pretty cool stuff. So I'm going to say match protocol, and the first protocol that I can match, and again, context-sensitive help reveals there's a bunch. But the first one I'll match is, we'll say POP3. And it takes a few seconds when you first turn it on, because in the background, it's checking to see if Cisco Express Forwarding, CEF, is turned on. And if it's not, it turns it on. Because CEF, that's required for NBAR to work. But the rest of the match statements should be accepted much quicker than that. I'll say match protocol again. This time it's going to be for my IMAP traffic. Let's do it again, this time for simple mail transfer protocol. And then finally we'll do Microsoft Exchange. And I'm done with my email class of traffic. Let's create another class of traffic. Let's do one for voice over IP traffic for the actual voice media. Again, I'll say class-map, but this time I'm not going to say match any or match all. I'd like you to know what the default is, though. The default is match all, but I'm only going to give one match criterion, so the Boolean logic doesn't matter. I've only got one statement that says match this, so the all or the any doesn't really matter in this case. I'm just going to leave it blank, and it will default to match all, but that's fine. And I'll call this voice, class map voice, and I'm going to match the protocol, as we talked about earlier, of RTP, the real-time transport protocol, and I could just enter that, and that would be accepted, but here's the thing. It's not just audio, it's not just voice over IP that uses RTP, streaming video does too. I would also be classifying video into this class of traffic. So we can be a bit more specific. I can say only RTP packets containing audio. We could get even fancier than that if we wanted to and say payload type, and we could specify a payload type which maps to a particular codec, but we'll just take all voice over IP traffic here. Let's enter that. And now let's create yet another class map. I'll say class-map. This time I'll do web traffic, and I want to be able to get HTTP or HTTPS. So I'll need to use my Boolean logic again of match any. I'll say class map match hyphen any, and I'll say web, and I'll match the protocol of HTTP, and I'll also match the protocol of secure HTTP. Let's do another one. This time, let's classify some undesirable traffic. I'll say class-map, and I'll just give one match criterion, so I'll not worry about match any or match all. I'll call this scavenger traffic. And I realize, as a disclaimer, I realize that a lot of companies use the BitTorrent application for very legitimate purposes. They can use it for their customers to transfer large files, but in some companies, BitTorrent is being used for nefarious purposes, like illegally downloading movies. But let's just say that in our company, even though BitTorrent, there's nothing wrong with it inherently, let's say that within our company, we've discovered a lot of employees using BitTorrent to download movies illegally, and we want to stop that. So what we can do is recognize BitTorrent traffic. I'll say match protocol BitTorrent. Typo there. Let's spell it correctly. BitTorrent. Again, a typo. Let's try it one more time. 2 R's in BitTorrent. You can tell I don't use that very much. Match protocol BitTorrent. we've now created a few class maps. Let's take a look at them. We'll say show class hyphen map, and we can see the email class of traffic and the 4 protocols that get lumped into that category, the web class of traffic for HTTP and HTTPS, secure HTTP in other words. Here's our voice traffic, and here's our, finally spelled it correctly, BitTorrent traffic. Oh, and notice this one, class-default. I did not create that one. That's the default class that I told you was there by default. If something does not get matched by anything that I created, any class map that I configured, it is going to be matched by this class-default class map. That was step 1 of MQC. In step 2 of MQC, let's create a policy map. Let's say policy-map, and I'll just call it demo. And not much happens here. Not much happens from this PMAP or this policy map configuration mode. The real magic, as I say, happens from policy map class configuration mode. From here, I'm going to say class, and I'm going to give a name of one of the class maps that I just created. Let's start off with email. That's the first one we created. And here is where I turn on one or more quality of service mechanisms. If I want to apply a marking, I could say set, and there's a variety of things I could set. I could say set DSCP. I could give a name or number, like I could mark email traffic with a value of, we'll say, AF12. I could do some queuing. Again, let's use some context-sensitive help. I could do class-based weighted for queuing by saying bandwidth. Let's do that. I'm going to say bandwidth 512. Now, the unit of measure here is kilobits per second. So what this command is saying, when I say bandwidth 512, a lot of people misunderstand this. A lot of people think that I'm setting a limit of 512K, but that's not what's happening. Here's what this command says. It says, I want to give this traffic at least 512K of bandwidth if it needs that much, and more if it needs more and more is available. Let me say that again. That's a big definition. I'm saying give this traffic at least. In other words, we're not setting a limit. I'm giving it at a minimum 512K if it needs that much. If it doesn't need that much, great. We can take that bandwidth that it doesn't need that's below 512, and I can let somebody else use it that might need it at the moment. But give it at least 512K of bandwidth if it needs that much, and give it more. We can go above 512K. Give it more if it needs more, assuming more is available. So again, one more time. This command says, give this traffic, give this class map at least 512K of bandwidth if it needs that much, and more if it needs more and more is available. Now, we also talked about weighted random early detection. Here's how we turn that on. We say random-detect. And if I just enter this is going to turn on weighted red, where it pays attention to. It sets those minimum and maximum drop thresholds that we were talking about. It sets those based on IP precedence markings. Those are older quality of service markings. Again, I encourage you to go check out my other YouTube video that deals with DSCP markings. We're much bigger fans of DSCP. It's a lot more granular. It's a lot more appropriate for modern day networks. So I'm going to add a qualifier here to say this is going to be DSCP based. So random-detect DSCP based. That turns on weighted red. But remember that we had a way to make weighted red more polite, for lack of a better word, where we just simply asked the other side to voluntarily slow down. That was explicit congestion notification. Here's how we turn that on. We're going to say random-detect ECN for explicit congestion notification. And I'm done configuring this class. Again, notice my configuration mode is policy map class configuration, not just policy map configuration mode. But I'll exit out of this and go into yet another class map. I'll say class. This time we'll do voice. And voice, it's latency sensitive. I want to send it first. So I'm not going to use the bandwidth command to configure class-based weighted fair queuing. Instead, I'm going to use the priority command to configure low latency queuing. I'm going to say priority, and then I'll give an amount of bandwidth. And maybe I've calculated based on the maximum number of calls that I anticipate and the codec that's being used. Let's say that I've calculated that I'm going to need about 768 kilobits per second of bandwidth. It gets to go first. So here's what the priority command says. It's different than the bandwidth command. The priority 768 command says, let this traffic in this class have as much as 768 kilobits per second of bandwidth if it needs that much, but no more. Let me say it again. Give this traffic as much as 768K. So the unit of measure is kilobits per second, and we're giving it as much as that. That's the maximum, but no more. We're setting a speed limit there. If we don't need that much, great. We can use that unused bandwidth for somebody else. But I'm saying give it as much as 768K, but no more, but let it go first. We're going to send up to a limit, up to a point. We'll send this traffic in this queue first. We'll start emptying out this queue ahead of other traffic types, but we're not going to exceed taking up more than 768K of bandwidth. And interestingly, that weighted random early detection tool I told you about, we can only configure the random-detect command in a class map where we've previously configured the bandwidth command. Now, we didn't configure the bandwidth command here because we wanted to use the priority command. Does that mean I cannot say random-detect DSCP based? That's right. Notice what happens if I try. It says, nope, you cannot do this. You've got to use the bandwidth command first, or also the shape command could be used, but you've got to use one of those commands before we turn on weighted red. So we're not going to turn on weighted red for the voice class. Let's do the web class next. I'll say class web, and this will be very similar to the email class of traffic. I'll use the bandwidth command again, and I'll say give this traffic at least 768K of bandwidth if it needs that much, and more if it needs more and more is available. I'll also turn on random-detection for DSCP-based markings, and I'll give the kinder and gentler variant of a weighted red by saying random-detect ECN for explicit congestion notification. And we've got one more traffic class to go, and that is our scavenger traffic class. Let's say class scavenger, and we'll enter that. Now here, I don't want to guarantee a minimum amount of bandwidth as we did with class-based weighted fair queuing. I want to set a maximum limit. I want to set a speed limit on this traffic. I don't want it to go first, so I'm not going to use the priority command. I'm going to use either the police command or the shape command. Well, I'm going to apply this to a fairly quick interface, so I'll use the police command. And I'm going to say police. Now, careful with this. The units of measure are changing on us. We can use context-sensitive help if we don't remember, but notice the units of measure are now in bits per second, not kilobits per second. So if I wanted to set the speed limit of 128,000 bits per second, I'll literally say 128,000 because the unit of measure is bits per second. Now, there are a lot of extra commands I could add on to this to say how we treat traffic that doesn't exceed the limit, how we treat traffic that does exceed the limit. We get into conforming traffic and exceeding traffic and even violating traffic, where we can have two buckets, and that's a big, long discussion on its own, which we'll not get into here. I'll just talk about the default behavior. The default behavior is if I just press enter like this, then it says if traffic does not exceed 128,000 bits per second, then I'm going to transmit it. And if it does, I'm going to drop it. That's the default behavior for the police command. And we've now completed step 2 of MQC. We've created our policy map. Let me show you a verification command. I'm going to say show policy-map, and it's going to show me my policy map that I just created that's named demo. And we can see each class that we created. Oh, and I'm glad I looked at this. It reminds me that I didn't actually give the priority command for the voice class. I was talking about it, and then I got off on that tangent of talking about how it doesn't work with the random-detect command. I actually didn't configure anything for voice. I need to fix that. So, good command to give. Let's go back into global configuration, and I'll go into policy-map demo, and then into policy map class configuration for the class of voice, and I'll say priority, and I'll make it, we'll say 768. Now, if I give the show policy-map command, you can see that it is doing something with voice. It shows the priority command. Awesome. Well, this is giving us an overview of what policies we have for different classes of traffic. Fantastic. And as the third step of MQC, we need to apply this policy map somewhere. And again, typically we do that to an interface. And I'm going to go into, on my router, interface gigabit 0/1. And I'm going to apply this in the outbound direction. Low latency queuing, class-based weighted fair queuing, they only work in the outbound direction, so that's going to be fine. I'll say service-policy, and I'll give the direction. I'll say it's output going out of this interface. I want to apply the policy map of demo, and we'll enter that. That's the 3 steps of MQC. There is my favorite verification command that I saved to last, though, and it's this one. It's show policy map interface followed by the interface identifier. We used gigabit 0/1. The reason I say this is my favorite verification command is it shows us the output from show class map. In other words, it tells me how I classify traffic. So it shows that for email, I'm matching POP3 or IMAP or Exchange or SMTP. It shows my match any logic. And just like the show policy-map command did, it shows me what policy I'm applying to this traffic. It shows me that I'm setting a DSCP marking. It shows me that I've got class-based weighted fair queuing configured. It shows me the number of times I've marked something with an ECN marking to say, hey, would you please slow down? So it's giving me packet and byte counts if I actually did have packets going into this queue. So it gives me the information that I got from show class-map, it gives me the information that I got from show policy-map, and it gives me bonus information. It gives me packet and byte counts to let me know that things really are being classified into this traffic class. So that's an overview of the three-step MQC process. Again, this is not some ancient process that I'm just telling you so you know about it. This is how modern-day utilities are configuring your router behind the scenes. If you're using auto QoS on a router in any of its forms, or if you're using EasyQoS and then you go look at the router configuration, you're going to see MQC. You're going to see this three-step MQC process has been performed behind the scenes, and I want you as a network professional to be able to go in and interrogate that auto-generated configuration and understand what's going on and understand how to make a tweak if you need to make a tweak, and even maybe how to set this up without the use of some other tool if you need to do so on a limited basis.